Welcome to today's paper reading. Today's paper is titled, NL2Contact, Natural Language Guided 3D Hand-Object Contact Modeling with Diffusion Model. This paper was published on AR14 by Zhongqun and Zhang and colleagues from the University of Birmingham and National University of Singapore. The abstract introduces the challenge of refining inaccurate hand poses and generating novel grasps in 3D hand-object reconstruction. Existing methods rely on geometric constraints that are not controllable. This paper presents NL2Contact, a model that generates controllable 3D hand-object contacts using natural language descriptions. The model addresses the complexity of cross-modal modeling and the lack of descriptive text for contact patterns. To support this, the authors developed Contact Describe, a dataset with hand-centered contact descriptions, generated by large language models based on specific prompts. The model's applications include grasp pose optimization and novel human grasp generation, both driven by textual contact descriptions. The modeling of physical contact between hands and objects is crucial for various applications including animation, virtual reality, and robotics. However, conventional methods often fail to accurately model human grasps, leading to unrealistic interactions. This paper introduces NL2Contact, a novel approach that uses natural language descriptions to guide the modeling of 3D hand-object contacts. This method allows for more precise and controllable contact modeling, overcoming the limitations of previous techniques that rely on high-level intent labels or coarse affordance regions. The proposed cross-modal latent diffusion model is designed to generate realistic hand-object contacts from detailed natural language descriptions, providing a new direction for research in this field. Figure 1 illustrates the NL2Contact setting, which involves learning to model 3D hand-object contact from a language description. This modeling of contact is utilized for grasp pose optimization. By leveraging the predicted contact to refine the initial grasp, the performance of NL2Contact surpasses that of contact opt and contact pose. It is important to note that contact pose annotations are derived from a motion capture system. In the field of hand-object contact modeling, previous studies have focused on grasp reconstruction and synthesis. These studies often infer contact patterns from hand-object point clouds using geometry constraints. On the other hand, text-guided diffusion models are probabilistic generative models that use a Markov chain to convert a simple Gaussian distribution to a target data distribution. These models have been applied in text-to-image synthesis and 3D generation of hand-object interactions. However, research specifically focusing on text-to-contact modeling remains relatively limited, with diffusion models being explored for controllable 3D hand-object contact generation from text descriptions. The Contact Describe dataset was created to address the lack of detailed text descriptions for 3D hand-object contact patterns. It is an extension of the Contact Pose dataset, adding annotations that describe contact patterns. The dataset features multi-level language descriptions, starting from high-level grasp actions, through middle-level grasp types and finger status, to low-level contact locations on hand joints. To generate diverse and natural language descriptions, the dataset leverages the ChatGPT-3 model, which provides feedback and assists in manual rephrasing of sentences. Figure 2 illustrates an example from our Contact Describe dataset, showcasing multi-level language descriptions. The dataset uses hand-centered contact prompts to generate detailed descriptions of contact patterns. These prompts are processed by ChatGPT-3 to produce multi-level and diverse free-form text descriptions. The high-level text describes the grasp action, the middle-level text details the grasp type and finger status, and the low-level text specifies the contact location on hand joints. This approach enhances the naturalness and diversity of the descriptions, making them adaptable across various object categories and attributes. Table 1 provides a comparison of intent labels across various datasets focused on hand-object interaction. It highlights that most existing datasets only collect verb-level intent labels, which are inadequate for prompting controllable contact modeling. In contrast, our dataset introduces the first detailed sentence-level contact descriptions, offering a more precise and comprehensive approach to understanding and modeling hand-object interactions. The NL2Contact framework is designed to model 3D hand-object contact using language descriptions. It consists of three main modules: text-to-hand-object fusion, stage diffusion module, and contact optimization. The text-to-hand-object fusion module extracts global features from both point clouds and natural language, fusing this information to guide the reverse diffusion process. The stage diffusion module generates hand-mano pose and predicts 3D hand-object contact maps, refining the hand pose through iterative optimization. This modular approach allows for efficient and accurate modeling of hand-object interactions based on textual descriptions. Figure 3 illustrates the NL2Contact pipeline, a novel method for modeling 3D hand-object contact using language descriptions. The framework consists of three main components: the text-to-hand-object fusion module, which efficiently fuses geometry information from point clouds and semantic information from natural language; a staged latent diffusion model that first generates the hand pose fitting the hand description and then generates the 3D hand-object contact map conditioned on the descriptions and the generated hand pose; and contact optimization, which iteratively optimizes the hand pose using the generated contact. Additionally, a switch is included to toggle between applications for grasp pose optimization and human grasp generation. The model is trained in an end-to-end manner, with a PointNet++ pre-trained on the contact pose dataset. During training, 2048 points are sampled from the object mesh as input. The optimization process uses the Atom Optimizer with a batch size of 64 and a learning rate of 1.5 times 10 to the power of -3. The training spans 50 epochs for hand pose denoising and 100 epochs for hand-object contact generation, taking approximately 11 hours on a single V100 GPU. The datasets used include the Contact Described dataset, which is an enhanced version of Contact Pose, and the Described HO3D dataset, which is used to evaluate the generalization capability of the method. Figure 4 presents a qualitative comparison of our NL2Contact method with state-of-the-art methods, ContactOpt and S2Contact. Our method stands out by generating accurate and controllable hand-object contact that precisely matches the input text description. In contrast, ContactOpt and S2Contact, despite being strong methods, tend to produce grasps where all 5 fingers are engaged, regardless of the initial hand pose provided. This behavior is evident even when a favorable initial pose is given, as seen in the first row of the figure. Our NL2Contact method not only generates more accurate contact but also ensures that the optimized hand pose aligns closely with the target hand pose described in the text, demonstrating superior control and precision in contact generation. Figure 5 illustrates the differences in grasp generation between Contact Gen 27 and our method. Contact Gen consistently produces grasps where all 5 fingers are engaged, which can limit the diversity and specificity of the grasps. In contrast, our method is capable of generating grasps that are directly aligned with textual descriptions, offering more control and variability in the generated grasps. This visualization highlights the superiority of our method in producing grasps that are not only diverse but also textually consistent, addressing a key limitation of existing methods like Contact Gen. Figure 6 illustrates the integration of our NL2Contact method with ChatGPT, showcasing interactive control for generating and refining grasps. In Part A, users provide high-level prompts, which ChatGPT translates into detailed contact descriptions. These descriptions are then fed into our network to generate the initial grasp. Part B demonstrates that the accuracy of the generated grasps increases as the text descriptions become more detailed. This integration highlights the potential for interactive and precise control in grasp generation tasks. Table 2 presents the quantitative results of grasp pose optimization on the Contact Described and Described HO3D datasets. The table highlights that the use of natural language guidance allows for the modeling of accurate hand-object contact. Specifically, the optimization from our predicted contact achieves the lowest mean per joint position error, MPJP, of 21.7 mm, outperforming other methods. Additionally, the table shows that contact descriptions significantly improve the generalization of our method to out-of-domain objects on the HO3D dataset. The results demonstrate improved contact quality metrics, including intersection volume, inter, of 7.1 mm3, contact coverage, cover, of 49.2%, and contact precision/recall, PR and RE, of 59.9%. These findings underscore the effectiveness of our method in refining hand poses and enhancing contact accuracy. Table 3 presents the quantitative results of grasp generation, highlighting our method's superiority over contact gen. 27. Our method achieves the lowest penetration, best contact, and highest diversity, as indicated by the metrics of intersection volume, 2.31, convergence, 5.89, and diversity, 5.91, respectively. This demonstrates our method's effectiveness in generating precise and diverse grasps. Table 4 presents an ablation study on the impact of multi-level text input on grasp precision and contact point location. The study reveals that the use of more low-level text descriptions results in more precise grasps and accurate contact point locations. Notably, even when high-level text is removed from contact-related descriptions, it still significantly outperforms the contact-opt method. The table also shows variations in MPJP, mean per joint position error, and contact quality metrics, intermediate, precision, recall, across different levels of text specificity. Table 5 presents an ablation study of our NL2Contact method, demonstrating its superiority over all other variants. The study evaluates the impact of different components, without text-guided, without text-to hand fusion, without text-to Ho fusion, without stage diffusion, with VE, and the full model. The results show that NL2Contact achieves the lowest MPJP and the highest contact quality metrics, indicating its effectiveness. Notably, the text-to-hand fusion module significantly improves accuracy by correcting initial inputs to fit gesture descriptions, and the stage diffusion model enhances performance by iteratively refining the contact map. These findings underscore the importance of these components in achieving superior contact modeling. In conclusion, this paper introduces NL2Contact, a novel cross-modal latent diffusion model designed for 3D hand-object contact modeling. The model is supported by the Contact Describe dataset, which includes detailed natural language descriptions of 3D hand-object interactions. NL2Contact has applications in optimizing grasp poses and generating novel human grasps. Looking ahead, the authors plan to explore the modeling of dynamic contacts using natural language, aiming to improve grasp stability and interaction capabilities through multi-level text descriptions. Thank you for watching.